All right. Good evening, everyone. Thanks for joining, Krishna Kumar. So I hope more students will join soon. But anyway, we'll get started with the today's session. So this is the last week of numerical methods course, and throughout 8 weeks, we saw how to solve different types of problems in different types of equations using numerical methods. So we saw for we started with how to solve linear system of equations, and then we got into finding eigenvalues of the matrix, and then we studied about numerical differentiations and then numerical integration, and before that we also did new linear interpolation, right? Sorry, just the interpolation between the values, how to do it numerically. Now as a final step in this course, we are studying about ordinary differential equations. However, numerical methods does not end here. This is an introductory, course to the numerical methods. Here we are teaching up to ordinary differential equations, but there are even more advanced. Even in ODEs, there are more advanced techniques that has not been taught in this course. Uh, but for that, you can take like a postgraduate level numerical methods course to understand it. So, in week 8's lecture, we saw about ordinary differential equation. Let me quickly go through what are the things we studied about ordinary differential equations. I hope most of you know about ordinary differential equations because you must have studied in other maths subjects, right? In fact, there is a dedicated mathematics course in engineering syllabus. So uh, the differential ordinary differential equations are you can write something like it is a function of x, y dash, y double dash, where x is an independent variable and y depends on x. If it is just f of x comma y, then it's just simply an equation. Now that equation, if it contains differential terms of y, then it becomes an ordinary differential equation. Okay. um, there is also other set of equations called partial differential equations, where you have multiple independent variable. For example, x and y both will be independent variable, and there will be another uh, function which will be dependent on both x and y. For example, if you take temperature field or electric field, so these fields vary in both x, y, and z direction. In that case, x, y, and z are independent variables which represents the spatial coordinates, and your temperature or electric field or whatever magnetic field, whatever you are trying to study, is going to vary on all three spatial coordinates x, y, and z, right? So then those will become um, dependent variable. So now your temperature field is going to be depend on both x, y, and z. I mean x, y, and z. And usually when you write an equation for this temperature and how it behaves, it becomes a partially differential equation, which means you will have gradients of temperature. You will have uh, you know uh, second derivative of temperature with respect to x, y, and z. So that is like more complex uh, uh, differential equations. We call it partial differential equations, and that is out of scope for this course. This course we study only ordinary differential equation, where you have one independent variable and one dependent variable, and that dependent variable depends on independent variable, and you know and in the equation you will have derivatives of dependent variable. You will be seeing derivatives of dependent variable. Okay. And uh, we also studied what is order and degree. So highest order derivative is that is called as an order, and the degree of the highest order derivative is called the degree of the differential uh, ordinary differential equation. Okay. And then we also study the classification, either it can be linear or non-linear. So um, if it is a linear, so if here you need to see a little bit different. There can be product of dependent variable and independent variable. So that doesn't mean it's a non-linear equation. But here the non-linearity is in terms of dependent variables. So if there is, let's say, y square or y dash, or let's say y dash y double dash. If you see these kinds of terms, then it becomes a non-linear differential equation. So in general, we say non-linear equations like if you have a cosine term, if you have trigonometric function, if you have hyperbolic functions, we call it non-linear equations, right? If you have exponential, we call it non-linear equations. But in terms of ODE, even if you find an exponential term, that doesn't mean it's a non-linear ODE. Although those are non-linear terms, but that doesn't classify as a non-linear ODE. Here the non-linearity is in between dependent variable and its derivatives. Okay, so that is the difference here, the non-linear equations and non-linear ODEs. Okay, and the nth order differential equation requires n arbitrary constants, which means you should provide n conditions in order to completely determine its solution, or in this case unique solution. Okay, um, and based on this conditions, you can divide it as either initial value problem or boundary value problem. In this course, we never went into boundary value problem, and it's a little bit advanced for this course. We limit our discussions with initial value problem, where the solution domain is open and all conditions are specified only at one single point. Okay, so that is the initial value problem, which means all the conditions y dash of x, so whatever the condition that you are going to specify will be specified at only one point, at x not equal to, let's say, 0 or -1, whatever it is. And from there you will kind of march from that x naught. You will go to x naught plus h, x naught plus 2h, x naught plus 3h. You will march in that dependent variable, that direction. Okay, so that's why initial, you can also say it's called marching problem. Here it's an initial value problem. Okay, and this is an very powerful technique, reduction of nth order ODE to system of first order ODE. We do a lot, let's say, in various fields. In all the fields it is applicable, um, but although we didn't get into much into this thing, uh, you just need to understand that whatever we are doing for one ODEs can be applicable for n number of ODEs. So if you have second order derivative, or second order different ODEs or third order ODEs, you can convert that into system of first order ODEs, which means you will have number of first order ODEs. Okay, so solving the system of first order ODE using the methods that we are going to use, let's say Euler method, or RK method, RK4, RK2, whatever the method that we studied, you can these methods are applicable for system of first order ODEs. Okay, so you can simply convert all the second order ODEs to second order or higher order ODEs to system of first order ODE, and apply whatever the methods that we are studying here. Okay, um, so that is the thing. So basically we write it each and every derivative as a separate variable. Okay, then this is one equation, this is the second equation. Similarly it will keep on going, and the final equation will have your exact ODE. Okay, so that's the idea. So you will have n first order ODEs. If you have nth order ODE, you can convert it into n first order ODE, where 1 to n minus 1 will be simply dy by dx equal to z1, dz1 by dx equal to z2, dz2 by dx equal to z3. These are all each and every equation. Okay, and your final equation, your zn, will be equal to the entire function that has been given. Okay, so this all these things you can convert and write it as a matrix. You can write it as uh, d capital Z by dx is equal to some capital F, where capital F include z1, z2, z3, z4 and these things, and uh, that will be your capital, the function f, and you apply Euler method for that. That's it. So you will apply it in a vectorized form. So that is usually we do, and in fact all the real systems will not behave like a first order ODE. It will all behave like higher order ODEs. So the ODEs will be more complicated to understand, uh, to analyze just with one equation. uh, so we convert that into system of ODEs and we apply the formulas. Okay. If time permits, we will look into how this can be done. Okay, today. Mm, and then we jumped into numerical methods on how to solve such systems. So we know how to solve analytically for a given. Let's say if dy by dx equal to f of x comma y, if it is a linear, we know how to solve. Like you can, if it is dy by dx plus px equal to q, if it is in that form, you can find the integrating factor and you can find the general solution, and then you give the initial condition to find the constants. So that's how we usually solve. But if your function becomes very complex, it is difficult to do it manually by hand. Okay, and that's why we prefer numerical methods. And the first method that we saw was Picard's successive approximation. So this is like it's not purely numerical, it is semi-analytical, because you will keep evaluating this function and you have to integrate this function analytically. So that's why it's an semi-analytical method. Okay, and also you analytically integrate the function, and you numerically do this iteration. That's why it's a semi-analytical. Okay, and then we went into this Euler's method. The Euler's method is a very simple method. You will have, so basically dy by dx is equal to some function of x. So now you are going to have a linear approximation from dy by dx, which means y at n plus 1 minus y at n equal divided by delta x is equal to h. So this is what is actually written in this form, where this delta x is nothing but h, your step size. Okay, so h times f time equal to yn. So basically, if your x is very small, your derivatives can be approximated as simply differentials, right? So dy by dx can be simply, if your delta x is small, this can be simply written as delta y by delta x, just the changes. So that's the idea. You can also derive the same thing from Taylor series. It's no big deal. When you have very fine delta x, this method will work better. Okay. So and also it has a order one, because when you do a Taylor series expansion for it, you will end up having the h square by 2 term left behind. So which means your order is 1 for Euler method. Now we saw that Euler's method is very bad, so we want to very bad in the sense you have to take very small step size to get accurate solution. Um, so we went with better methods. One of the method is quadratic Taylor method, where instead of stopping at in Taylor series, instead of stopping at first derivative, we also include the second derivative, that's quadratic. And similarly, we can also go with higher order methods by including as high orders as possible. But the only drawback is you need to find this derivatives at each and every at that data point. Okay, so which means at x naught. So what is given is y at x naught is equal to y naught is what is given. So that is the initial condition. But what you also need to know is second order derivative. First order derivative is given by the equation itself, so function f of x comma y, so that is known. Second order derivative, we have to differentiate this f of x comma y function to find d double dash, and then similarly you keep differentiating until the highest order, and you use this method to solve it. So that is also one of the way that we can solve. So that will improve our um, what do you call predictions. So in that way your error becomes second order if you use quadratic. And the next one was we studied was Euler's modified method. Actually this is a class of there are class of predictor corrector methods, and one of them here is the Euler modified method, where you predict a value, and using the predicted value you correct your solution. Okay, so initially you predict the value with whatever the function you have, and based on this predicted value you substitute in this equation to find the corrected yn plus 1. Okay, and this also gives a better uh, you know reduced error, which means it also you can take a much higher time steps compared to Euler, this Euler modified. Okay, so this is also called, I think, some other name also it has, like I think, I'm not really sure, you can check the notes. So this is Euler's modified method, and then finally we also, not finally, this is other class of methods are Runge-Kutta methods, where you have we generalized, so all these things, this predicted character methods, we kind of derived it, like how to obtain a better, more accurate solution. Now here what we did for, let's say I want order m accuracy. Now if I want to do that, what are the predictions and corrections I need to keep making, how many steps I can take forward to get a more accurate solution. So for example, if I want a RK method with an order m accuracy, then I need to do these corrections for m times, and we have generalized it as omega. So basically we have to find this additional k on top of y naught, which is going to be which should be as exact as possible. Okay, so this k naught can be represented as like this, where omegas are arbitrary constants, we don't know what the constants are, and it may or may not agree to a certain equation, or it may or may not be dictated by the equations. So k1 is can be written like this, and k2 is like small increment in h, and also using this a newer uh, you know a better estimate of y in the function evaluation, and you keep doing it again and again for mth order, and then finally you expand, you substitute all this in here, you expand it as y1 equal to y naught plus k. Instead of k, you substitute this whole relation with k1, k2, k3 and k4, and equate that to this y1 can be represented as a Taylor series, right? Equate those two, and you will end up having some equations using which you can find these uh, constants. Now you may not have enough equations to find constants, so sometimes what you can do, you can arbitrarily choose a constant. Let's say omega 1 I chose to be 1, or omega 2 I chose to be 1 by 2. If you choose some certain amount of constants, and the remaining constants should be dictated by those equations from the Taylor series, and that is how you get alpha 1, alphas, betas and omegas. Okay, and based on these arbitrary constants, you can get different set of RK methods. Okay, and each are valid unless it satisfies the equation that the Taylor series predicts. Okay, so if I want to go with RK, with order 2, then I will take only K1 and K2, whose constants will be, which I need to evaluate will be omega 1, omega 2, alpha 1, beta 1, 1. So 4 constants I need to evaluate, and order is 2, so you will have 3 terms in the Taylor series expansion. Now you uh, compare the coefficients of y dash and y double dash, you will be end up uh, getting this as your uh, RK of order 2. Okay, so so that is how you find k1 k2. Once you find k1 k2, you substitute in this k, which is half, where omega 1 is half and omega 2 is half. Okay, and then we get the y1. So for each and every each and every step, what we have to do is we have to evaluate for k, k1, k2, and then substitute that in this relation. So similarly, we can also go for RK4, like four orders accurate, fourth order accurate, where you will evaluate k1, k2, k3, k4 in this manner, and then substitute in this equation, then finally you will have uh, of that steps y. Okay, and this is even more accurate of order h power 5. I mean, error is in the order of h power I, which means it is fourth order accurate. Okay, so these are RK methods. Usually people use RK2 and RK4 maximum. No one, sometimes RK3 also people use, but RK4 is the most famous, everyone uses. All right, and finally we also saw multi-step method where till now we were using only the one step. For example, to evaluate y at x naught plus h, we used only y at x naught. Now, if you are going to y at x naught plus h, if you want to find y at x naught plus h, we will use y at x naught minus h, x naught minus 2h, and also its derivatives if we want. Okay, so these are multi-steps methods. Like whatever the step values that I have, I'm going to use it for my benefit. Okay, to get a more accurate solution. So in this case, you have at y at n plus 1, I can use n minus 3, n minus 2, n minus 1, and n data to get y at n plus 1. Okay, so this is also a predictor corrector method, Milne's predictor corrector method, where predictor, uh, you know, uh, um, predictors formula is this, and then corrector formula is this, and the associated error terms. If for some reasons, if you don't know what is, so these are all having starting problems. For example, if a differential equation is given, and only one initial condition will be given. So let's say y naught is equal to uh, y at x not x equal to 0 is equal to some value is given. Now, but what you don't know is y at x x plus h, x naught plus h, x naught plus 2h, x naught plus 3h, all these things we don't know. So only if we know three steps, we will be able to employ this method. Okay, so these methods has a starting problem, which means you have to use some other method to find these three steps. So that could be either Taylor's method, Taylor series method, or Euler's method. You can use to find the first three steps value, and later from the fourth step, what you can do is you can use this Milne's predictor corrector method. But what is also true is your first three, the error added or error introduced because of using a lower order method in the first three steps is something you cannot get rid of. That is the only problem. So we have to use most accurate method. Let's say RK4 does not have a starting problem, so you may need to use RK4 for the first three methods, and later you can use Milne's predictor method uh, you know uh, for predicting further steps. Okay, so those are the some introductions. So similarly, there are multiple predictor corrector methods. It's just not limited to Milne's predictor method. There's also Adam Bashford method. Um, it's famously used, and there are multiple predictor corrector methods depending upon the order that you want. Okay. So for simple problems like dynamics in let's say equations of motion, if you want to solve, let's say in robotics, if you want to solve them, there you may not require very high order of accuracy. RK4 may be enough. But let's say if you're solving for uh, trajectory planning, for satellites or for rockets, while in those equations, those for especially for satellites, what you do is the orbit calculations require you to solve ordinary differential equations, and there you cannot have, you need an accuracy up to the decimal of 12th decimal. So there you will go for more accurate methods. So that's where this predictor corrector methods will come, more accurate methods will come. Okay, so depending upon the applications, the methodologies keep changing. All right, any problem, I mean any doubts you guys have till now? So if there are no doubts, I am going to solve only one problem today, but I think that will itself take enough time. Um, so today I have a linear ODE and its initial condition we have. We are going to solve it using different methods and see how the errors are different, how different they are compared to an analytical method. So this is an linear ODE. So this we can easily solve using analytical method. And we will also evaluate the same thing using numerical method to understand how these behaves. Okay. So today we will focus on just four methods: Picardo's, Euler's method, RK2 and RK4. I think that is sufficient uh, for you guys to solve at least the assignment problems. Okay. If you have any questions, please stop me anytime. Um, Let me check my recordings. Okay. So what we were asked to find is we have this ODE dy by dx equal to minus 2y minus cos 4x, and the initial condition y of 0 is equal to 3. Okay, and we were asked to find solve for, or maybe I will just write find y of zero point 0.4. Okay, we need to find y of 0.4, and let's say our step size we will take it as h is equal to 0.2, which means we need to do two steps. So in general, these kinds of ODEs is not usually written as dy by dx. Sometimes in physical systems, if you look at it, it will be like dx by dt. So for example, your independent variable will be time. So in that case, what are you doing is you start from an initial condition where at time t equal to 0, we know how our system is, and we derive equations of motion, how the system would behave in time t greater than 0, and we will solve this equation of motion for t greater than 0. So that's the basically idea. That's how the physical systems, that's how we solve it. So in that case we say instead of x it will be t, and we'll say it's a time marching problem, which means we are marching in time from t equal to 0. We are marching in time. Sometimes what is also true is sometimes we do space marching, which means um, we know this is our x domain. So at x is equal to 0, we know some value, and we know the system how it behaves along the space, and the ordinary differential equation is going to describe that system, behavior of that system along space, and we will try to solve each and every delta x by going one step at a time, so step by step. So that's why it's called space marching or time marching problem, or in general these are marching problems. So again here what we are going to do is at x is equal to 0, we know y is 3, and the system is going to behave like t like this. So we will take one step at a one step at a time, like when y equal to 0 0.2, what is the value, and from y equal to 0 0.2 to 0 0.4, what is the next value. Okay, so uh, so basically these are again marching problems. Okay, so let's begin with Picard's method. So in Picard's method, again, here also you can do, why don't we, yeah, let me write down the equation, how we should solve it. So it's a successive approximation method where you will write this as, so this is your iterative, uh, function. So y at n plus 1th iteration of x is equal to y naught plus, y naught is the condition that has been given. Okay, integral of x naught to x function of x naught and y at n of x, sorry, dx. Is that right? Yeah. Okay, so now in this Picard's method also you can take a step-by-step approach. So initially we will solve from let's say we'll go from x is equal to 0 to zero point 0.2, and then from point 2 we can go to point 0.4. That is also we can do, but it involves lot of integration and things like that. So what I'm going to do is I'm going to take a shortcut. I'm just going to take, just for this Picard's method, we will take the step size to be zero point 0.4. I'm just going to evaluate directly from 0 to zero point 0.4. I will leave, um, you know, 0 to 0 0.2 and 0 0.4. I will leave it up to you. You guys, do it in your free time and see how the answers are different. So let's first solve this so you will get an idea what is going on. So this is our, uh, you know, equation. This is what we need to apply iteratively to get the solution. So what is our function? So in all this, if you remember, it's nothing but dy by dx is equal to some function of x comma y. So this function is nothing but uh, minus 2y minus cos 4x. Okay, so let me write down the function x comma y is minus 2y minus cos 4x. Okay, so and our x naught is going to be 0 and x is actually zero point 0.4, and y naught is 3, that is also given in the question. Y at x naught is equal to 0 is 3. So if this is the case, let's write down the formula. So y at n plus 1 is equal to y naught plus integral of x naught, let's say it's 0 to x. Function is minus 2y minus cos 4x, where y is the previous iteration value yn times dx. Okay, now we need to evaluate the integral analytically, so that's why it is called semi-analytical. So let's do that. So y naught plus, this is y at n plus 1 as a function of x. We didn't substitute the 0.4 yet, so what this would be, so 2 into yn. So yn is an numerical value. It is a constant here. It is not, although y is a function of x, here we have substituted yn. So I'm just going to simplify it a bit. So here we will substitute the previous iteration value of y here, and then we integrate it. Okay, that's the difference. If it is simply y, you have to consider y as a function of x. So you will have y times dy by dx. Here it is a constant. Okay, so if you don't understand, please let me know. This is an important thing to understand. So 2yn and only x will be there, minus integral of cos 4x is going to be sine 4x by 4, evaluated from 0 to x. So this can be written as y naught plus minus 2y n x minus sine 4x by 4, and if you substitute 0, it's going to be simply 0. I'm just going to leave it like that. Okay, now you know y naught. So now let's write y at n plus 1th iteration at x is equal to y naught is 3 plus minus 2 y at previous iteration value x minus 0.25 sine of 4x. Now for we need to find for x is equal to 0.4. Let's substitute that x is equal to 0.4. So y at previous y at new iteration value y at n plus 1 of 0.4 is equal to 3 minus 2 into y at previous iteration value times 0.4 minus 0.25 sine of 4 into 0.4. Okay, so this can be simplified and written as, how can we write this? So these are just a numerical value, you can add them together, and please remember to use radians in sine and cos evaluations. 2.253. So this is coming out to be 2.7501 minus 0.8 y at previous iteration value. Okay, this is our iterative function. We haven't begun iteration, we just evaluated integral. Now we need to do iteration for this function. Okay, once a given once ODE is given, you first find the integral function. I mean, first integrate it and find the iterative function, then you keep iterating. Okay, now your first iteration will be like, what is your first iteration? Y of 1 at 0.4. I'm going to drop 0.4 here, is equal to 2.7501 minus 0.8 into y at 0 iteration. 0 iteration is nothing but your um, initial value. So here it is 3. Okay. So if you substitute that, this comes out to be 0.3501. Okay. Now your second iteration is going to be simply 2501 minus 0.8 times y of 1. So you just repeatedly substitute whatever the value that you got from the previous iteration until you see some convergence. Okay, so 0.3501. So how much will this be into 0.8? 2.7501. This is going to be 2.47002. Okay, now your third iteration is going to be y of 3 is 2.7501 minus 0.8 into 2.470. So this will be 0.7741. You can also note how the iteration values keep changing. So from it started from 0.35 and then suddenly jumped to 2.47, and then again you jump back to 0.77. So clearly it hasn't reached the steady value. So we have to continue this. So if you continue this, this will be 2.7071 minus 0.8 minus 0.7741. So that will be around 2.1308. So I actually did this, and at y of 5 I got something like 1.0454, and then 1.9138, and then 1.2191, 1.7748. So it kept on going, and let's say this is 3, right? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So around like 31 iteration. I'm not going to do it in front of you, but you can do this around roughly 31 or around that. Okay, at 0.4 it reached to a value called around 1.528. Okay. So so basically the previous 38 iteration was also giving 1.528. The 31st iteration was also giving me 1.528. So I stopped there. Okay. So you have to continue doing this iteration by substituting it again and again. And at the end, at 31st iteration, you may reach 1.528. So that is the problem with Picardo's method. You have to keep doing iteration. You have to wait till convergence um, to reach this value. Um, and if you do have a multiple steps, as I said, so instead we directly jump to point 4, right? So let's say I first jump to point 2, okay, and then I evaluate the y. After doing all this iteration, I evaluate at point 2 and use that as a new value. Again I do it for y of point 4. Again I integrate this function, find the iterative function, and then again if I do the iteration, uh, then again you have to take, let's say, like 30 iterations or so to reach a converge value. So each and every step size that you take, it will take enormous amount of time to find the uh, solution. So that is one of the problem with the Picardo's method, and also it involves evaluation of integral. So we are doing numerical methods because sometimes our problems are very complex, and this method actually goes against this overall motivation of doing numerical methods. We do not want to see any analytical in our system. Okay. It is actually useful when you are dealing with analytical systems, and if you want to get some closed form solution or something, but this is typically not used in the in actual, at least in the field of numerical methods. Okay. So the homework is, please do this. If now take step size to be, take step size as h is equal to zero point 0.2, and then um, evaluate y at 0.2, and then use this as your y naught. Okay, y naught is y at 0.2, and then evaluate, use Picardo's method and evaluate y at point. Okay, and see how the value is different. So for example, I tried to evaluate, but I'm not really confident on my results, but it was giving a closer result. So I am getting y of 0.4 to be 1.3881, but please verify this. Okay, and it is so this is after taking two step size. After taking h is equal to 0.2, which means I also know y at 0.2. So y at 0.2 was something around 2.014. Okay, so after taking step size, I was able to reach to 1.3881. But we don't know whether this 1.528 or 1.3881 is accurate solution or not, because we don't know the solution, right? So why don't we derive an analytical solution for this? Since it's a linear equation, we all studied how to derive an analytical solution for this simple ODE. So this is dy by dx equal to minus 2y minus cos 4x, right? So this you can rewrite it as dy by dx plus 2y equal to minus cos 4x. So if you see, this is in the form of dy by dx plus px equal to q, right? So this is a linear ODE. So what we will do, we will first find the integrating factor. So what is the integrating factor here? E power integral of p dx. So in this case, your p is 2, and sorry, this should be py. Q is a function of x. So your p is 2, and q is minus cos 4x. Okay, so if this is the case, what happens to your integral of p dx? And yeah, integral of 2 dx is equal to e power 2x. This is your integrating factor. And what is your general solution? Y into integrating factor equal to integral of q into integrating factor plus c. This is your general solution, right? Now if you substitute it, c we will evaluate based on the initial condition. Y e power 2x is equal to integral of minus cos 4x into integrating factor is 2x plus c. Okay. Okay, I forgot to put dx here. Dx plus c. Now what you will do, e power 2x is equal to minus integral of e power 2x cos 4x plus c, correct? So now you need to integrate this e power 2x cos 4x. How will you do? For some reason I'm not able to hear you properly, Damodar. Can you? I still couldn't hear you properly. But I think whatever you are telling, um, is it related to UV method? So you can use UV method to solve. Okay, so probably that's what Damodaran is telling. So you can use UV method or power rule uh, to solve this. What you will have is e power 2x and cos 4x. E power 2x cos 4x both are indefinitely differentiable. So what you will do is you have to write I is equal to integral of e power 2x cos 4x. Okay, and when you do UV method, you will end up having some terms plus integral of e power 2x cos 4x, which is nothing but your I. Okay, so you club them, you rewrite this as an I, and then you club them, and finally you will be able to find out e power 2x cos 4x dx to be something like e power 2x cos 4x by 10 plus e power 2x sine 4x by 5 plus c. Okay, so I will you know give that as an exercise, so you verify this thing. Okay, this is your integral of e power 2x cos 4x dx. So now let's substitute it here. Y e power 2x is equal to this integral we know minus e power 2x cos 4x by 10 plus e power 2x sine 4x by 5 plus c. Okay, so this c you can couple them, so that's not a big deal. So now you can take e power 2x to the other side, and you can write y to be y is equal to c e power minus 2x minus uh, cos 4x by 10 plus sine 4x by 5. Okay, So this is your general solution. We need to know C. What we will do, we will apply boundary condition, or in this case it's an initial condition. Apply initial condition where y at x is equal to 0 is 3. What happens? This becomes 3 is equal to c e power 0, which is basically 1. So we'll just write c minus cos 0 is 1 and sine 0 is 0. So this will give you c to be 3 plus 1 by 10, which is 31 by 10. Okay, so your final solution is y is equal to 31 by 10 e power minus 2x minus cos 4x by 4, sorry, 4x by 10 plus sine 4x by 5. So this is your final solution. So for this we were able to find the analytical solution. Now what you need is y at 0.4. That's what we are comparing. Y at 0.4 is 31 by 10 e power minus 0.8 minus cos of 1.6 by 10 plus sine of 1.6 by 5. How much is this? If you guys have the answer, please let me know. Okay, I am quicker than you guys. So it's 1.1959. Okay, so this is your analytical solution. 1.1959 is your analytical solution, which means this is accurate solution, and our results has to be somewhere near. So if you look at it, so exact solution is 1.1959. Okay, but Picard's method gave you 1.5, what was it, 528. Okay, with the step size of taking 0.4. But if I do the same thing with h equal to 0.2, then I'm getting 1.3881, so which is much closer to 1.1959. So that's the point. So if you reduce the step size, if you reduce it even further, you will be able to reach the exact solution. But this requires a lot of calculations. That's the problem with Picard's method. Now let's do Euler's method, and then we'll see RK methods also, and you will understand how you will understand its advantages basically. So first, let's do Euler's method. So in Euler's method, as I said, you will have only the function evaluation. So in this case, y1 is going to be y naught plus h into function of x naught and y naught. Okay, this is also called Euler explicit method. Um, you know, it's also called backward Euler method, because you're trying to use previous values y naught and x naught to find new value. Okay, And all these methods that we studied in this course is actually explicit methods. There are also implicit methods which are much mm, you know much greater, which has much greater accuracy, and it gives a bounded solution. Yeah, but those are very advanced topics, that's why we are not discussing here. Okay, anyway, now if we take the step size to be zero point 0.2, we need to evaluate y at 0.4. So we need to do two steps. We need to take two steps. And our y naught, so let's take the first step. First step is go from x is equal to 0 to 0 0.2. H is 0 0.2. X naught is 0. Y naught is, what is y naught? Y naught is 3. Okay. And y1, which is nothing but y at 0 0.2, is nothing but y naught plus h f of x naught comma y naught. Okay, y naught is 3, we know, h is 0 0.2, and the function is, let me write on the function here again. Function f of x y is minus 2y minus cos 4x. Okay, so this will be minus 2y naught minus cos 4 x naught. Okay, now you just need to substitute it, and that is the value for y equal to 0.2. 3 plus 0.2 into minus 2 into 3 minus cos, oh, x naught is 0, so this is going to be simply 1. So this whole thing will be minus 7. Minus 7 into 0.2 is minus 1.4. So 3 minus 1.4 is 1.6. So this is the value. Y at 0.2 is equal to 1.6. This is the value from Euler's method. Okay. So we will take the second step now using these as a value. The second step is to go from x is equal to 0.2 to 0 0.4. Okay, and here your x naught is 0.2, your y naught is previous value, which is 1.6. Okay, and step size is 0.2, of course. So you can write y at 0.4, which is equal to y1 is equal to y naught plus h f of x naught comma y naught, where x naught and y naught is different now. This is equal to 1.6 plus again h is 0.2. We're again taking the same time step, and the function is minus 2 into y naught. Y naught is 1.6 minus cos 4 times x naught. X naught is 0.2. Okay, that's it. Now you need to evaluate this one, this value. That will be your y equal to 0.4. Let's try to evaluate that. This is 1.6 plus 4 into 0.2 cos into minus 1 minus 2 into 1.6 into 0.26. So this is around minus 0.7793. So finally you end up having 0.8206. Okay, this is your y. This is y at 0.4 from the Euler method. Okay, and the exact solution y at, let me not use y star, let me just use y exact. Y exact at point 4 is 1.1959. Okay, you can see how big the differences are. Okay, now let's see how RK2 method will work. I hope this is clear. How we should be straightforward. You just need to evaluate the function at x naught and y naught, and then you substitute them in the formula. You will end up having the y value, and now use this new x and y values for the next step. That's how we solve it. Okay. All right. Next thing is RK2 method. Okay. Um, Now in RK2 method, uh, let's go back. In RK2 method, you have to evaluate K1, K2, and you evaluate K from this K1 and K2 and substitute in Y naught in the Y value. Okay, Y function. So basically you will have Y1 equal to Y naught plus K, and K is equal to half K1 and K2, K1 plus K2. K1 is nothing but h into function of x naught and y naught, and K2 is h into function of x naught plus h and y naught plus K1, right? Yeah. So you evaluate K1, K2, substitute it, you will end up having the result. Again, we are going to take two steps. Okay. Here, the first step is to go from x equal to 0 to 0.2. I mean, just to explain, I'm writing this, but it's not required. Just for better understanding, I'm doing this. So your x naught is 0, y naught is 3 as usual from the initial condition, and f of x we know. So initial first thing what you have to find is h is 0.2. Again, the step size we are going to keep same. H is 0.2. Now let's evaluate k1. K1 is h times function of x naught and y naught, which is equal to 0.2 into the function value is minus 2y minus cos 4x. Okay, if you substitute it here, minus 2 into 3 minus cos 0, which is same thing, so it's going to be minus 7. Minus 7 into 0.2 is minus 1.4. This is your k1. Now k2 is h times function of x naught plus h plus y naught plus K1 by just K1. Okay, so this becomes 0.2 into minus 2 y naught plus K1, where this is y naught plus K1 minus cos 4 x naught plus h. Okay, this will be equal to 0.2 into minus 2 into y naught is 3 plus K1 we just found out to be minus 1.4, minus 1.4 minus cos of 4 into x naught is 0, h is 0.2, so we'll just write it as 0.2. Okay, how much is this? So this is 3 minus 1.4 is 1.6. 3 minus 1.4 is 1.6 into minus 2 minus cos of 4 into 0.2 into 0.2. So this is coming out to be minus 0.7793. Okay, now your k is going to be half of k1 plus k2, which is half minus 1.4 minus 0.7793 is equal to point minus 1.0897. So your y1 is equal to y naught plus k, where y1 is nothing but y of 0.2 is equal to y1 is equal to y naught is 3 minus 1.0897, which is around 1.9103. So this is at y equal to 0.2. What we need is y equal to 0.4, so we'll take the second step. The second step is from x is equal to 0.2 to 0.4. Now your x naught is 0.2, y naught is 1.9103. Again your h is 0.2. Now let's evaluate the evaluate k1, k2. K1 is h into function of x naught and y naught, which is equal to 0.2 into minus 2 into y, which is 1.9103, minus cos into 4 times 0.2. Okay, and this comes out to be, I directly substituted the formula, so because we all know what is the function value, just to avoid repetition I just substituted the formula. So if you substitute this, you will end up having minus 0.9035. That's the answer. Okay, similarly I can do k2, which is x naught plus h and y naught plus k1. Okay, now this becomes 0.2 into minus 2 into y naught is 1.9103 plus k1 is minus 0.9035, minus cos of x naught plus h is 0.2 plus 0.2, which is 0.4, cos of 4 into 0.4, 4 into 0.4. Okay, now let's evaluate this. This is around minus 0.3969. Okay, now let's find k. K is half of k1 plus k2, which is equal to half of minus 0.9035 minus 0.3969, which is equal to minus 0.9035 minus 0.3969 divided by, this is minus 0.6502. Okay, now your y of 0.4, which is equal to y1, is equal to 1. Y naught plus k, which is y naught is 1.9103 plus k is in negative, minus 0.6502. So this is around 1.2601. So this is your final answer. So for example, let me write it down. X, y. So x 0, y 3. X 0.1 was sorry, x 0.2 is 1.9103. 0.2 is 1.9103, and x at 0.4 is 1.2601, and the exact value is 1.1959. So although we did a lot of calculation for Picard's method, we were still, our error was much greater. Now for RK2 we didn't spend much time, but we were able to get a closer value. Okay, so this is much better compared to previous one. There is also one more method called modified Euler method, if you remember. So in the class notes, you have Euler's modified method. Now, um, this Euler's modified method you have here. This is a predictor corrector method. Is actually same as RK2 method. You can find the equivalence here. So basically this K1, what we found, h times f of x naught y naught, is what actually is the predicted, and the predicted value is substituted it here. Okay, so this is nothing but y naught plus this is K1 is what we substitute here, y naught K1. Okay, so you can actually derive the equivalence between modified Euler and RK2 method. So which means if you even if you use modified Euler, it's going to give you the same results. Basically, they both are one and the same. Okay, you can verify that. I hope RK2 is clear. We have to evaluate K1, K2, substitute in the you know main formula. That's it. All right. So what is remaining? Um, so we did Picard's method, Euler method, RK2. Now finally we will do RK4 method. Okay. So the RK4 method, as the name suggests, you have like it is a fourth order accurate. It is expected to have even lesser error, and you will have 4Ks to evaluate. Okay, so let me write down it. Y1 is equal to y naught plus k, where k is equal to 1 by 6, k1 plus 2k2 plus 2k3 plus k4. Okay, now k1 is same as the Euler's method K1, which is h times f of x naught y naught, and k2 is h times f of x naught plus h by 2. So this is like an half step. uh, so while taking a full step, we are also taking an half step in between. So x naught plus h by 2, y naught plus k1 by 2. Okay, let me check. Okay, yeah, and k3 is h times function x naught plus h by 2. Now we correct at the half step, k2 by 2, and then we take the remaining step, h is h into f of x naught plus h plus y naught plus k4, sorry, k3, sorry. Now once you evaluate these k, you substitute it here and substitute this whole k into y, you will end up having the y for that time step. Okay, sorry, I keep telling time step, but here it is not time step. Say it's for that step. So the first step, as I said, we are to going from 0 to 0.2, and x naught is 0, y naught is 3, h is 0.2. Let's evaluate k1. K1 is h times f of x naught y naught. This we already know. So h is 0.2. So you can see for all these methods, we maintained step size to be same as 0.2 in order to have a valid comparison. Here it's going to be 2 times 3 minus cos of 0. This is going to be minus 7 into 0.2 minus 1.4. And k2 is going to be h times function of um, x naught plus h by 2, where here x naught is 0. Okay, let me write that down. Y naught plus k1 by 2. So which means 0.2 into some function of minus 2 into um, y naught is 3 minus 1.4 by 2 minus cos of 4 times x naught is 0, h by 2 is 0.1, cos of 4 times 0.1. Okay, now we can evaluate this. 4 times 0.1 cos of minus 1. This is 2 minus 2 into answer minus 2 into 0.7. 3 minus 0.7 is 2.3 into 0.2, which is minus 1.104 minus 1.104. Okay, now we need to find k3. K3 is h times function of x naught plus, again same h by 2, y naught plus k2 by 2, which is equal to 0.2 into minus 2 into 3 minus 1.1042 by 2 minus cos of 4 times 0.1. Again it's 0.1. So if you evaluate this, you will end up having minus 0.874. Okay, so k1, k2, k3, oh sorry, no, this is minus 1.1634, and you have k4 finally, h into function of x naught plus h, y naught plus k3, which is 0.2 into minus 2 into 3 minus 1.1634 minus cos of 4 into 0.2 now, because it's no more h by 2, it's just h. So this is around coming around 0.874. Okay, now let's find k. K is 1 by 6, k1 plus 2 k2 plus k2 k3 plus k4, which is around 1 by 6 into minus 1.4 minus 2 into 1.1042 minus 2 into 1.1634 minus 0.87. So k is around minus 1.13486, and finally you can write y of 0.2 is equal to y naught minus 1.1386, or y naught plus k is equal to 3 minus 1.13486 is equal to 1.8651. So this is at y equal to 0.2. Now we need to do the same thing for y equal to 0.4. Let's do it. Second step, where x varies from 0.2 to 0.4, x naught is 0.2, y naught is 1.8651, and h is 0.2. Okay, now let's evaluate k1. K is f function of x naught y naught, which is 0.2 times minus 2 into 1.8651 minus cos of 4 into 0.2 Okay, and this will come out to be minus 0.8854. Okay, and k2 is h times function of h by 2 y naught plus k1 by 2. I will just directly substitute it here, minus 2 into 1.8651 minus 0.8854 divided by 2 minus cos of 4 into, now y naught, sorry, x naught is zero point 0.2 and h is 0.2 by 2, so it's going to be 0.3. Okay, so this k2 will be 0.6414 if you do the calculation. And similarly k3 we can do, k3 is going to be 0.2 times minus 2 into 1.8651 minus 0.6414 by 2 minus cos of 4 into again 0.3. K3 is also h by 2. This is equal to minus 0.6902. So finally we can also write k4. K4 is again 0.2 times minus 2 into 1.8651 minus 0.6902. Here you do not have division by 2, and finally you will also have 0.4 here. Okay, so this will be equal to minus 0.4641. Okay, finally you can write k to be 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4. So this comes out to be 0.6688. I'm just giving you the numbers to save some time. And finally we can write for 0.4 to be 1.8651, sorry, 8651 minus 0.6688, which is equal to 1.196. This is what you get from RK4 integration after doing this for two steps for point when you take 0.2 as your step size. So let's write this down in as a table. It will be a clear understanding. So 0, 3 is the initial condition given, 0.1, 0.2. Let me write it as RK4. Okay, 0.1 was, how much was 0.1? 1.8651. Sorry, 0.1. 0.2 and 0.4. 1.8651, and this is 1.1963. Okay, this is RK4. Similarly, we can also, let's write RK2 here. First value we can eliminate. This was 1.9103. This was 1.2601. Okay. Euler method was how much was Euler method? It's 1.6 and 1.1959, sorry, 0.8207. And finally the Picard's method also I will write down here. Y is 3. So this one, I think we didn't really do each and every step size, so let me write down finally. We directly went here 1.568. However, your exact solution should be, sorry, however your exact solution is at 0.4 is 1.1959. So we can see for the same step size, RK4 is able to give a very good approximate. So that's why people typically just blindly use RK4 wherever they want to use. provided your step size is enough. So for this case, we took a step size of zero point 0.2, and uh, we were able to get a more accurate solution compared to any other methods. So that is the takeaway. We can also do the same thing for different methods like there's also RK3. Although we don't know the exact formula, you can find it in internet. There's also predictor corrector methods. We can keep doing it. So but after RK4, uh, the gain in accuracy you're going to get is very less. Already you are like in the order of in the around, what is the difference? It's 0.0004. So uh, so after RK4, your methods become more and more complex, requires more and more function evaluations. Right? So the to time consumption in the sense whatever, not what we are calculating by hand. Typically, these methods are programmed in the computer, and so for RK4, you require how many function evaluations? You need to, so this function will be this will be a separate function as a program, and you have to give x naught and y naught. It will return a function value, so that each function evaluation is like a so it's an operation that a computer does, right? So in RK4 you need four function evaluations. So in RK2 you need only two function evaluations. So as your method becomes more and more complex, your function evaluations keeps increasing, and the amount of accuracy that you get will keep diminishing hereafter. So it's like a diminishing returns. It's a point of diminishing returns. So that's why people stop at RK4. If they want, if the system requires you to go for more accurate methods, then people do people spend enough time to use some other different method. So here the function evaluations becomes when to fold. So, but when you use RK4, it's primarily reliable whenever you encounter in real scenario. Whenever you encounter to solve any ODEs, you can, if you are using RK4, people will accept it. Okay. All right. Any questions regarding the methods? I hope it is as clear as possible. But if you have any questions, please feel free to ask me. We didn't really, solve any problem for multi-step method, but I think there is already one problem solved in the class, so you can use it as a reference, and similar problems you can solve in the textbooks. Okay. All right. Any questions? I said that I think so. Let me also give you a quick idea of how to do this. So we said we will briefly discuss about the reduction of higher order derivatives and how to solve using these methods, right? So, for example, let's say um, you have you have second order derivative, or let's say third order derivative, y triple dash plus 3y double dash plus, I'm just randomly using the numbers here, y dash plus 4x plus e power um, 4 plus e power 2x plus minus 9 equal to 0. Let's say this is your differential equation. This can be your differential equation. Okay. Now solving this is going to be very difficult. So what people do is they convert it into a system of first order ODEs. So how do we do it? So here your uh, independent variable is x, your uh, dependent variable is y, right? Now what we can do is we can write z1 to be let's say y, okay, and z2 to be dz1 by dx, Now if you differentiate z1 in terms of y, then it becomes dy by dx, which is nothing but y dash. Okay, now you can write z3 to be dz2 by dx, which is nothing but d square y by dx square, which is equal to y double dash. Similarly, we can write z power 4 to be y triple dash. Okay, now or what we will do, we will write, sorry, we'll write it like this for easier understanding. So z2 is z1 and z3 is, so first we will write z1 to be dy by dx, which is y dash. Okay, or you can do it in the other way, the previous way also, whatever I said. So now what you can do is this y triple dash is nothing but minus 3y double dash minus 5y dash plus sorry, minus 4x minus e power 2x minus 9. Okay, now we can write y double dash as minus 3z2 minus 5z1, correct, and then minus 4x minus e power 2x minus 9. Okay, now you can write it as uh, now you can write it as y dash. So this is what we need to evaluate. So we can write it as z1 z2 z3 as a vector, which is equal to y dash y double dash and minus 3z2 minus 5z1, correct, minus 4x minus e power 2x minus 9. Okay, so this we can write it as z1 and z2. I'm just writing it as same. Now how do we write? Now let's say you have the uh, variable y to be y y dash y double dash. Okay, now dy by dx, it's a vector equation, dy by dx is nothing but your y dash y double dash y triple dash, which is nothing but z1 z2 and z3. Okay, so finally you can write this as d capital Y by dx is equal to z. Okay, so you capital write it as capital Z equal to z1 z2 z3. So now you can write dy by dx equal to capital Z, where capital Z is equal to z1 z2 and you know z2 minus 3z2 minus whatever it is, minus 3z2 minus 5z1 blah blah blah. Okay, now this is a vector, this is the first order equation, sorry, this is the system of first order ODEs. Okay, now let's say you want to apply a Euler method to solve this. Okay, how would you apply Euler method? So what is Euler method? We have
y, now everything will be a vector now. So y1 is equal to y naught plus h into some function of x naught and y naught is what we write, right? So in this case, this function is nothing but your z. Okay, so z, which is a function of going to be your y naughts. Okay, y naught and x naught. X naught is one value that we know, and y naughts we can use this. So now you write this for first one. So what you can do is you can write for the first equation. So this is all is a vector, right? So um, so this is like y dash at 1, y double dash at 1, y triple dash at 1 is equal to y dash at 0, y double dash at 0, y triple dash at 0 plus h into z1, z2, z3. We know z1, z2 is nothing but y dash and y double dash. So this is z1, z2, and z3. So here, if you notice, we need to know y dash, y double dash, and I think it should be y, y dash, y double dash at 1. Similarly, here also you have y naught, y naught dash, y naught double dash. Okay, so now you notice that you need three more conditions, and we know that this is a this is the uh, third order differentiation, right? So if you go differential equation, if you go back, that is one of the point. So if it is an nth order differential equation, you need n continuous, you need solution will have n arbitrary constants. So to find a unique solution, you need n conditions. So in this case, since it's a third order derivative, you need to give y naught is just not enough. You also need to give y naught of dash and y naught double dash. Okay, so given that we know that, so this vector we know, okay, and this vector we can find. Okay, this is just a function, right? You just evaluate it, and that's how you find y1, y1 dash, y2 dash, and you keep doing this again and again for each and every time step, sorry, each and every step. That is how you integrate this entire third order uh, you know ordinary differential equation. So these kinds of system that you will see in for example, let's say you are doing some combustion calculations, you will be asked to find what is the species, like chemical species, how it is getting produced, how it is getting destructed, all these things. If they want to find out, every species will have its own ODEs. So now these are coupled systems. So for example, in z3 is a function of z1, z2, and x. Okay, so which means this is coupled with z1 and z2. So you have to similarly in a chemical species, the species getting consumed is going to be dependent on what is going to get produced. Okay, or the species that is going to get produced is going to depend on the species that is going to get consumed. So these species concentration will be these things C1, C2, C3, and you need to solve it you know uh, together. Okay, coupled approach you need to take. Yeah, so these things comes in it's a little bit advanced, so that's why we didn't go much in this course. But you can extend this approach. I mean, the methods does not change. We have same RK4. We can, instead of Euler, we can simply use RK4 here also. So RK4 is applicable everywhere. So in that way you can solve uh, those systems too. Okay, so I do not want to confuse you by bringing up big things, so I thought I will restrict myself. I will not show any calculations for this higher order ODEs. But yeah, I think whatever the problems that we solved today should be uh, helpful for you to solve the assignment problems, your assignment 8 problems. Okay. Um, if you have any questions, please feel free to stay back and ask me. If not, we will wrap up this course. So I guess there is going to be one revision session, probably, maybe on coming Wednesday. You will know if there is any revision session. We will just revise the entire, whatever has been taught, what are the important equations, all these things we will revise. But anyway, I will also upload this class notes for you to revise it on your own. So that is also fine. But I would encourage you to, take uh, take notes by yourself. Okay. Yeah. Anyway, all right. Thanks for joining. If you have any questions, please stay back and ask. If not, I will meet you in revision session. So Lavanya has some doubt. I have one doubt. I need to know about exams. Yes. What do you need to know about exam, Lavanya? Um, is she here or no? Okay. I think you are muted. You can unmute yourself and ask, or you can also type it in the chat. It's fine. I am guessing she's typing. So the coming exam is online. What is the total marks? Um, mm, I think it is 50-50, right? It shouldn't it should be there. It should be in the uh, website itself. This is mm, courses. Will it be one word or problem solving? So it will be problem solving. It will be same as your assignments. Whatever you did in your assignments, it will be same as that. But you need calculator. I think in the exam, you will have uh, inbuilt calculator in your exam screen. Okay. You will not carry physical calculator, but you will have the inbuilt calculator. But they will always give you. Uh, you can take your pen papers. They will give you to do some rough calculation, so it should be fine. So where is the exam? So I think exam is around like 75%, the final exam, and your assignments will be best 6 out of 8. That will be for 25%. Okay. So I think September 20 is the exam. Okay. All the best for you guys for the exam. Um, so so typically, you might expect. So you just need to remember some formulas, how to solve them. It is not that difficult, um, right? Uh, but mostly you can also expect some questions that I have solved, uh, and some questions that has been asked already in the assignments, so that may repeat. Uh, it may repeat. I'm not really sure, but it is going to be in a similar manner. It will be easy. You no need to worry about it. It is just the point is to test how much you understood in the numerical methods, right? So that's it. Um, yeah, just uh, understand the methods. What are the different methods that we used, and it should be fine. All right, I study will pass the exams. See, assignment questions will be a good exercise for you to remember some things, but it's also a good idea to solve some exercise problems from the um, from the books. You can also use books to solve some problems to make yourself familiar with the uh, you know familiar, and make yourself quickly adapt with the methods that have been given. And time will be sufficient. It will be same as your assignment. Your assignment is not that difficult, right? Is it difficult, your assignment? How many marks are required? I think for pass mark, so so average assignment score should be about 10 out of 25, and the average exam score should be about 30 out of 75. Then only you will be receiving the certificate. Although it's 40, it is true, it's 40 out of 100, but assignments also you should score at least 10 out of 25, and exam should be about 30 out of 25. Those two individual constraints that you have to satisfy in order to get. If one of the two criteria is not met, if you look at it here, if one of the two criteria is not met, you will not get the exam certificate. It's not just 40 out of 100. Okay. And yeah, I think this is going to be online. I don't think so. It is a written exam. Um, I think it is an online exam. So you must have received a communication regarding this from NPTEL. Have you not? If you have registered for the exam, you must have received communication regarding this. It is going to be similar to this. You have to go in person, but you have to take online exam in the exam center. Okay. Mostly it will be like that. But you will also receive the communication. I didn't receive though, but if you're still confused, you can write to NPTEL, um, or you can also use this common forum to ask. Okay. I think it is online. Yeah. All right. Thank you. Each problem takes minimum 20 minutes. Uh, I mean, see, within 3 hours, 50 problems. 50 problems, that is not, see, they may not give that many problems. So, first of all, um, is it said that it's, 1 second? Here is about course. See, final exam, they may not be giving like, so they may give, let's say, like 20-30 problems also. That is also, it's fine. 21 mark and 15 2 marks. Did they release the, when will the hall tickets be released? Okay, 21 mark and 15 2 marks. See, mostly, they will take care of that. You no need to worry about the time. So they will make sure that you will complete your, exam within 2 hours. And so so they will take the question paper in such a way so that you will get an additional 1 hour, uh, you know, to do it. So usually they prepare like that. So you no need to worry about it. Even if it is 50 problems, it will be simple problems. Some of the problems will be simple. Okay. it will not take like 20 minutes. So one or two problems might take like 20 minutes, but yeah. So hall tickets, I'm not really sure. These you can, if you would have registered, you should be receiving so. Okay. So before you will receive the hall tickets. Model question. Um, I mean, the model question is same as your assignments. It will be same as. I do not have any more questions. But if you're, you can use textbooks that has been given, right? You can use one of these four textbooks. There will be enough problems for you to practice. So it's not going to be, so I am solving like a full problem, like until you reach convergence. For example, there is this Picard's method. I solved like 31 iterations. But the other Euler and these things I use like two time steps, right? So sometimes they will give like in first step, what is your final answer? That would be the solutions that they will look for. So they will not let you do this iterations to very high value. So in that way, it should be fine. There is, unfortunately, there is no demo test. um, don't it's fine. I I do not have previous model question paper also. What you could do is you can actually um, you know ask in the common forum. So the NPTEL team would be able to help you if the request is legitimate. So that you can do. You can always ask about this, inquire about this in the common forum. Um, uh, so I'm not sure there is any what do you call, the previous model question paper, or they don't usually release it. I haven't seen in any other courses, so I'm not sure about this numerical methods, but you can sure ask for it. And we okay, you have already sent feedback. Okay. Yeah, they will consider it is. So since they are handling this large amount of courses, it would be little difficult to implement it right now. They if since you have sent it as a feedback, they might implement it from the next course onwards, if they find the proper way to do it. But you don't need to think to this level. uh, so the model questions are going to be same as your assignments. There's also good chance that the same problems will get repeated. Okay. So whatever the assignments, you just go through the assignments once, solve them once, and a little bit more calculations that you can do with those assignment problems itself. You should be fine. You will be easy. It will be easy for you to take the exam, so you don't need to worry about it. Okay. All right. All right. Thank you, Damodar. Thank you, Punguri Sindhu. Thank you, Pradeep.
Thank you, Pradeep, and thank you, Pumudi. So I'm really glad that you guys enjoyed my live sessions. If you have any doubts, or if you want to discuss course content, you can also contact me via my email. I can also type it down here. And also, you guys no need to call me sir. You can just call me Ganesh. That is fine. No, I mean, I have completed my PhD, but I'm not in the stage of professor. So, all right. Thank you guys for attending. Hopefully, I think there will be one revision session, um, and you will soon receive a notification about it. Yeah. If you are free, please feel free to join. And if you have any questions, you can ask. Thank you very much. See you.